Hi, everyone. I'm really happy to open the machine learning track today. And during the next 30 minutes, I'll talk about experiment tracking and how to do it with Git. So first, a bit about myself. My name is Eryk, and I work as a data scientist at Bol, which is the largest e-commerce platform in the Netherlands. Outside of my work, I also write articles about data science. This actually led me to publishing 2 editions of my book. And in my spare time, I like to read and play video games. So we have a few things planned for today. We'll start with the reason why we should track our machine learning experiments. Then I will tell you why I think DVC is a good solution for this problem and how it actually works. And we'll wrap it up with a live demo during which I will run a few experiments. As we know, building a machine learning product is a highly iterative process. Before finding a good solution to our problem, we might try out tens or maybe hundreds of approaches. And even pushing the deploy button does not mean that our work is over. Most likely, we'll continue running experiments to try to improve the performance of our model. And as data scientists, I think we know how to come up with lots of cool ideas for experiments. We might be inspired by a blog post we read in the morning, or maybe the latest research paper we've seen on Twitter. And then we'd like to run some experiments really quickly. However, that often comes at the price of reproducibility. That is because in order to iterate fast, we have a tendency to cut some corners. And instead of doing that, we should try to make sure that those two are not mutually exclusive. So at some point in your career, you might have heard a similar story. Your colleague tells you that some time ago, which knowing our luck is a long time, our team ran a very successful experiment with a much better score than the current model. We are asked to find out what we did differently back then. And ideally, can we do that before the end of the week? So the story can also have some further modifications. Like for starters, the colleague that worked on the problem might have already left the company. Or we might have entirely changed our approach to the problem 2 or 3 times since then. And my personal favorite, the CSV file that we are using as the input from the business was updated, meaning overwritten, dozen times. And of course, we do not have previous versions of the file. So I hope that after hearing stories like that, we are all determined to keep our experiments fully reproducible. So the first solution to this problem might be an old school one. We can simply track our experiments on sticky notes or in a physical notebook. Clearly, that's not a very scalable solution. And once the stickies go to the bin, we can't really recover them anymore. So another approach would be to use the good old spreadsheet. There, we can track quite a lot of things. We can filter the rows or maybe sort the observations by the score. But while this is already better than the stickies, we are still missing a few things in our logs. For example, code version or model version, or maybe a few more error metrics. You might say that this is a simple problem. Well, as we are already in a spreadsheet, we can simply add more columns. And you're fully right. However, this quickly becomes hard to manage. And it is very error-prone. And I don't think I have to convince you that logging those last 2 experiments on Friday at 4:45 is probably not close to the top of the things that you want to do. So given those ideas do not work that well, you're probably thinking that there must be an already established, ideally out-of-the-box solution for this. And indeed, that's the case. So it turns out that there is quite a lot of these solutions available out there. And I have probably missed quite a few of those here. So the question becomes now, which one to choose? This might be a tough decision because we need to consider pros and cons of all of them. For example, the vendor lock-in problem, ease of maintenance, associated costs, or security. So for example, we might not want to send our data or metrics to any external services or databases. So today I want to show you why I think DVC is a good solution for tracking our experiments. First of all, I really hope that you are already tracking your code with Git. And DVC is an open source tool that builds on top of Git. So to work with DVC, we do not need a dedicated metric server. In terms of storage, it works with all major providers, so AWS, GCP, Azure, or even Google Drive. DVC is basically a command line tool, and the commands are very similar to the ones from Git. And what is even better is that there is a dedicated VS Code extension, so we can do all of those things with a few clicks in a friendly UI. And lastly, DVC is actually very flexible and super easy to start with. So we can start prototyping and tracking our experiments in a matter of minutes. So the basic approach to running a reproducible experiment pipeline with this setup would be that we track our code with Git, and all the other things present in a data science workflow with DBC. So this includes hyperparameters, metrics, data, machine learning models, and any other artifacts that we might want to track. So now that we know that we can use DBC for reproducible experimentation, how does that actually work? To understand the entire workflow, we need to focus on 3 elements. We'll start with versioning data and artifacts. Then we'll discuss the pipelines, which help with making sure that all the steps of our experiments are fully reproducible. And lastly, I will show how running experiments works in practice. To understand how data versioning works, let's assume that we have an already existing project on our machine. In that project, we have a script training a model using 2 CSV files. And by the way, all the principles we discuss here regarding these files, they also apply to any other artifacts we might want to track with DBC. As you probably already have guessed, we do not want to track those files with Git. So that's why we initialize a DBC project in our directory. This creates a local cache on our machine. And once we start tracking the data directory of DBC, the data files in our project will be ignored, and Git will track the new file instead. The new file is called data.dbc in this case, and it's a placeholder or a pointer to the actual data's location in the DBC cache. So as you can see, to create a pointer, DBC uses a hashing function. In this case, it's MD5. As the new file is a small text file, it can be easily versioned with Git. Well, the actual data will be stored somewhere else, and under the hood, DBC will make the connection between the file's metadata and its actual location. As I mentioned, we use the pointer file to find the actual data files in the local DBC cache. So far, so good. Let's create a new experiment right now. So for example, let's assume that we received a new CSV file from our stakeholders, which we should use instead of the first CSV file. In our project, we simply replace the file. Then we tell DBC, hey, the data in the directory we are tracking has changed, and the pointer file needs to be updated. So a new hash is generated, and it once again points to the cache. Here, we can already see a very useful capability of DBC. It does not duplicate files unnecessarily. So the second data file that is common in both experiments is stored only once, as it has not actually changed. So this might seem as not that significant, but let's imagine a case with 100,000 images, and that we manually edit maybe 10 of those. In such a case, we definitely do not want to fully duplicate the entire dataset to track these 10 extra images. So that's almost it. We already know how the tracking happens. So far, the cache is located locally on our machine. That's great for quick experimentation and prototyping. But at some point, we might want to actually store some of the versions of our data, or maybe the entire project, in a more persistent place. For example, somewhere where it can be also accessed by other team members. As such, we can also have a remote storage and push the data files there. As I have mentioned already, this can be any of the cloud providers, a private server, or even a local directory if we want it to be. So we already know how tracking works, and the next key component is the DBC pipeline. The pipelines make sure that the entire experiment is fully reproducible, including code, parameters, data, models, and so on. So as you can see, we have defined 3 stages in a YAML file. And again, this YAML file is a text file, so it can be easily versioned with Git. Breaking it down a bit, our pipeline actually consists of 3 steps: preparing data, training a model, and evaluating its performance. Each step is essentially a Python script, a separate Python script. In the pipeline, we additionally provide each step's dependencies and its outputs. As you can see, the output of some of the steps is directly used by the next steps. And the outputs of all the intermediate steps are versioned with DBC. Again, any small text files are versioned with Git, while other artifacts are tracked with DBC. So now that we know how tracking actually works and how we can use the pipelines, we are getting close to the demo part. So as a data scientist and a gamer, I always wanted to play around with Pokemon dataset, so I'm really glad that I finally had the opportunity to do that. And for those who are not familiar with Pokemon, it's a series of video games. In those games, you basically catch creatures called Pokemon, train them, and battle other trainers to become the very best. As you can see, there's a lot of different species of Pokemon, and the image does not even cover all of them. So right now, we have around 1,200 unique Pokemon in total. So the task for today will be to classify each Pokemon as a legendary Pokemon or a normal one. In short, legendary Pokemon are the rare and strong ones that you might get a single chance to battle in a game. So, and to classify them, we'll use their stats, such as attack, defense, or hit points. And for the case of the demo, DBC is already set up in this project, but there are links to tutorials on how to do that at the end of the presentation. I will switch to VS Code right now. And here I will show you all the files that I have already mentioned during the presentation. So we start with the parameters file, where we store the parameters for each of the stages of the pipeline. So in this case, we have we store parameters for two stages, preparing data and also the training part. Here, for example, for data, we include the test size, or maybe if we want to include mega evolutions of Pokemon or not, for training some parameters of machine learning models. Then we have the DBC pipeline that I have already mentioned. In general, DBC is a command line tool, so there are multiple ways we can create the DBC pipeline. We can either do it using the command line, or we can also just manually type in the contents of the file in a YAML text file. In this case, I went for typing it manually, and you can see that we have the 3 steps that I already described during the presentation. So preparing data, training a machine learning model, and evaluating its performance. For each of the steps, I specify what is the script, what is the Python script that is used to run it, what are the dependencies, what are the outputs, and also if there are any other things that are that need to be considered. So, for example, the parameters. And one thing to note here that I haven't mentioned before is the metrics at the end. So by default, DBC tracks a metrics.json file, which is an output containing the metrics of our model. And it tracks it the same way as it automatically tracks the parameters file. But there are also different ways to add a bit more custom metrics to for DBC to track, and I will show those in a second. So I will just quickly go through all the steps of the parameters of the pipeline, but again, this is a very simple project, so you'll see that there's nothing fancy here. It's just loading a few steps, training a model, and outputting the performance. So for the prepare data step, I just load the parameters from the parameters YAML file. I read the CSV file, do some basic filtering based on the parameters, and create the train test split also based on the parameter, and store those into the process data directory. In the train step, I basically, again, load the parameters, load the process data set, instantiate a LightGBM classifier using the parameters from the params YAML file, train it, and output the model in the models directory. One thing to note here is the extra step of DBC Live. So DBC Live is a helper library which works as a machine learning logger. So I mentioned that DBC automatically tracks the metrics file as the output of the metrics, but we can also log a lot of different things ourselves. So in this case, I'm using a DBC Live callback. So the DBC Live is integrated with quite a lot of different machine learning frameworks. And in this case, it's like GBM, but it also works with XGBoost, PyTorch, Keras, and any other libraries out there. So in this case, what it will do is it will track the evaluation loss over the training steps. And then additionally, I also store and track a feature importance plot in the form of a static image. The last step is the evaluation step, in which I, again, load the model, load the process dataset, create predictions. And again, using DBC Live, I store quite a lot of different things. So I store a confusion matrix, an ROC curve, and a precision recall curve. And I also store the metrics that I mentioned before in a metrics.json file. So that's basically all the files that are here. As you can see, it's quite a simple workflow, just to give an example how it works. Now I will show a few ways how to run the experiments. So the simplest way to run an experiment in DBC is to go to the parameters YAML file, change one of the parameters, so let's say maxdef to 10, save the file, and in the command line, run DBC experiment run. So as you can see, the experiment will start running. And one very interesting thing to note here is that it says stage prepare data didn't change skipping. What it actually means is that there is smart caching under the hood for all the pipeline steps. So if we trigger the entire pipeline and maybe 2 out of 3 steps have not changed at all since the last run, and this includes any of the inputs, parameters, or code, DBC will simply skip those and pick up the outputs from the cache. This way, it just works faster if we, for example, have a costly training stage that we do not actually want to run. So the experiment finished. We can now quickly look at some results. So if we, as I mentioned, DBC is a command line tool. So if we run dbc x show, we will see a table. And here we see three things. So the workspace, which is basically our current directory, the main, which is the branch, and also an experiment. If I now go over the table, you can see that it tracks quite a lot of things, but I will explain those in a slightly different way that will maybe be a bit more interactive. So for now, I will exit this. And we can run experiments in many different ways. I already showed you the one, I think, the simplest one. Another one is we can manually type in the command, so dbc experiment run, use the set parameters flag to actually indicate which parameter we want to change. And let's say we want to change the train parameters and max dev to, I don't know, 17. Okay, there is, of course, a typo here. So it is set param. I hope this will work. So as you can see, the value in the parameters YAML file was updated automatically, and DBC is running another experiment now without any input from myself. In the meantime, another way of running experiments is to use the VS Code command. So we can use the dbc command modify workspace parameters and run. And then we have an interactive tool which we can use to select which parameters we want to change. So let's say that for the sake of this experiment, I will pick the mega evolutions, modify this one. It was false. I will include those in our dataset. So basically what you see is that this is an interactive way of writing the command line command automatically. So now that the experiment is running, I already hinted that there is a DBC VS Code extension, which makes our life much easier. So let's go there. And let's start with the experiments. So experiments is basically a table that I already showed you in command line, but displayed in a much more interactive way. So we have 3 elements here with the Git icon, and those are basically the commits to the Git repository. You also see those experiments here, Urban Jump, Extra Vega, and some other ones. Those are the experiments I ran just now. What is important to notice is that those experiments, they are not Git commits. So DBC under the hood uses Git references. I will not go into much detail what those are, but I will link to an article explaining that. So with those Git references, we can run hundreds or thousands of experiments without actually committing all of those different branches to our Git repository. This way, we are skipping cluttering, and well, we can only promote whichever experiment we want to an actual Git commit. So in this case, let's see what we have here. So we can see that in the source area, we are tracking 3 different Python scripts. The evaluate script changed a bit in between runs. We can also see the models. Of course, the model was trained each time with different parameters, so we can see there are different versions of those models. The process data changed for the latest experiment only, and that makes sense because I changed the mega evolutions file in the prepare data step, which means that basically another data set is created, which is slightly larger. And we have then all the parameters that we use for the models, the metrics that we store, so their performance, and also the metrics calculated during the training step with DBC Live. So this, of course, is fully interactive. So let's say that I don't really care about raw data because I know that it will not change. I can hide it. Or maybe I think that, let's say, the order of the columns here is not really right. I can change those however I want. Okay, it's not. I can reorder those as I want. And one more thing, I can also remove experiments. If, for example, I already run dozens of experiments. I don't want to keep some of those. I can just easily click on them and then remove the selected experiments from here. One more thing is that now I have a few experiments. Let's say I want to find the one that has the best recall score. I can go there, sort descending to find the one that works best. In this case, it seems that the best experiment is, well, mine and also the other one. So now with one click, we can apply those changes to the workspace. So our current directory will contain all the information that is on this branch, including parameters, code, data as well. Or if we are already happy with this experiment, we can create a new branch, promote it to a Git commit, and do a pull request or merge request, depending whether you're using GitHub or GitLab. In this case, yeah, let's apply this to the workspace, and I will also do some cleaning up of the experiments so we don't have those here. Okay, I need to remove the sorting for that, and then I can remove those. Okay, but actually first, before I remove those, there's one more extra important thing that I forgot to show, which are the plots. So in the plots, we see all the things that I also wanted to store during the presentation, during the run of the experiment, during experimenting. So the first plot is basically the loss function over training. So here I can see how the loss function changes as the training proceeds. It's extra useful for long training processes because this plot is updated live as the training proceeds. Then I also have the ROC curve and the precision recall curve I wanted to store. The confusion matrices, so I can also see which model performed best, or maybe which one had more false positive or false negatives. And also the feature important plots stored as static images. And I can, of course, like if I don't want to see all of the experiments, I can just remove those and compare the ones I actually want to see. So in the interest of time, I will maybe not go fully over grid search, which I also wanted to share, but I will very briefly mention that you can use the command line commands that I mentioned before to run a queue of experiments. So you can, instead of running them as they go, create a lot of them, queue them. They will pop up in the experiments table as waiting or pending. And then using DVC experiment queue start command, what you will do is you can start all the experiments. They will run sequentially, and then you can compare the results in the table. And of course, DVC also provides some functionalities to parallelize this process. And at this point, you might also ask, but well, this is exhaustive grid search. Can we do something smarter? So of course, we can change the script to be a random grid search. But what we can also do is we can use libraries such as Optuna, which are integrated with DVC. So we can also track all the trials for Optuna using DVC. So I will now go back to the presentation to wrap it up, to also leave some time for questions. So yes, Git combined with DVC provides an efficient environment for machine learning experimentation. With Git, we version code, configurations, and any small text files such as metadata pointers. With DVC, we can version all the other artifacts. This includes data, and also create reproducible pipelines. And lastly, with VS Code, or with the VS Code extension, we get a user-friendly interface for experiment management and also visualizations. So as I mentioned before, I believe the biggest advantages of this setup are twofold. So first, our experiments are fully reproducible. And second, we can set everything up in a matter of minutes. So here I will list some references which you might want to check out regarding the workflow I have presented today. So for example, how to start everything from scratch. And that will be all for today. So thanks a lot for listening. You can find me on LinkedIn or on Medium. You can also check out my book or use the QR code to access the repo containing the code base of this project. And I will leave it at that and answer any questions that might pop up.
Thank you, Eryk. That was awesome. I
Thanks
think
a lot.
we've got some questions in our Q&A portion. I'll read them out and let you answer them.
Sure.
First question from Alexander. There was an example with data versioning where we add data to DVC history. Is there a way to completely remove artifacts from history, considering that we can process real users' data and we should comply with GDPR? I'll also post the question in chat as well.
Yeah, that's a good question. To be honest, I don't fully know. So for all the projects that I worked with, those were projects that were personal projects. So I wasn't working with any GDPR compliant data, but I do believe that there must be functionality for removing those.
All right, thank you. And also from Alexander, they asked, is it possible to use DVC with GitHub Enterprise?
Yeah, so you can use DVC with, well, any kind of Git provider. So it can be GitHub or GitLab. You can also use GitHub Actions, for example, to make sure that the pipeline is triggered whenever you commit any new code to your code base. So you can definitely integrate GitHub with DVC.
Nice. And then final question that I have, oh, just kidding, there are more coming in.
Okay.
Another question from Gabriel. What about deployment? For example, comparing it with MLflow and other frameworks.
Sure. So DVC, at least in this scope, is mostly used for experimentation. But Iterative, which is a company standing behind DVC, they also have a suite of different products. So they have a product used, well, for deployment of ML models and also for the CI/CD of those models. So there are different tools in the, let's say, DVC ecosystem or iterative ecosystem that you can use for those.
Nice. All right, and then another one from Ross Coleman. I'm just going to keep coming rapid fire at you.
Sure, definitely.
Yeah, next is DVC pipelines versus Airflow versus Prefect. Do you deploy DVC pipelines to prod? PROD?
That's definitely a very good question. So the difference between Airflow or Prefect or DVC pipelines is that those pipelines, so DVC is not a scheduling tool. So this is not a tool that I would use to actually put things in production or run those pipelines, like literally use this YAML file to run the pipelines. The reason is that they are used for experimentation, and like tools like Airflow and Prefect, they are used for scheduling those tasks so they execute in a particular day, in a particular frequency, and so on and so on. So I would use a different tool for scheduling those. So you can, of course, schedule them in the same order that they are in the YAML file, and you can use the YAML file to build your scheduling. But for the scheduling itself, I would use other tools that are tailor-made for that.